Number 59. In terms of the bonds present, explain why acetic acid, which is CH3CO2H, contains two distinct types of carbon-oxygen bonds, whereas the acetate ion, formed by loss of a hydrogen ion from acetic acid, only contains one type of carbon to oxygen bond. And the skeleton structures of these species are shown. So this one on the left-hand side is acetic acid. We can tell that this is an acid because acids will always have one more hydrogen than its counterparts. So in this case, you have 4 hydrogens, 1, 2, 3, and 4. The other one has only 3 hydrogens, right? So the one that has more hydrogens is always going to be the acids. These are conjugates of each other, but that's not until later chapters. So this one has to be acetate ion. Okay, so now they're saying that acetic acid has 2 distinct carbon to oxygen bonds, and the acetate ion has only one type of carbon to oxygen bond, and we just got to figure that out. Now they give us the skeleton structures, which means that they're not the real Lewis structures, but in order to truly figure out this question, we got to learn how to do the Lewis structures, right? And you got to write the actual Lewis structures for acetic acid and acetate. So let's start with acetic acid. Acetic acid. So I'm just going to write the backbone. So we have H, C, H, H. There is a single bond, then an OH, and then there's an oxygen. Okay. So remember, carbon wants to have 4 valence electrons and oxygen wants to have 6. So for carbon, for this one, there was 1, 2, 3, 4 valence electrons, so that's all accounted for. But for this one, there's only 3, 1, 2, and 3. So there's one lone electron that needs to do something. So let's look now. Oxygen should have 6 valence electrons. So 1, 2, 3, 4, 5, 6. And then this oxygen has 1, 2, 3, 4, 5, 6. So look at this oxygen. This oxygen has 2, 4, 6, 7 valence electrons. Remember, we're always looking for the octet rule, which means that most electrons want to have that 8 valence electrons at the end when they're sharing. So since this oxygen only has 7, it's probably going to want to bind with another electron. And this carbon only has 7. 2, 4, 6, 7. So what's going to happen? This electron is going to bind with that lone electron and turn it into a double bond, just like that, right? So that's basically the Lewis structure. This oxygen is okay because it has the octet 2, 4, 6, 8. So that's all good. So I'm just going to, actually this is fine. I'm not going to redraw it and waste your guys' times, right? So in this case, it looks like I have a C that is clearly double bound to an oxygen. And then I have a C that is single bound to an oxygen that has an H. So those are your 2 distinct carbon-oxygen bonds. So I have a C double bonded O and a C single bonded O. Now let's draw the acetate ion. So I'll just put acetate ion. And they gave us the backbone. So let's see. HCCO. And these have hydrogens. And this has hydrogens. And this has the oxygen, right? So just like before, we just have to take into consideration what electrons were left out. So there was 1 electron left out from this carbon. And this oxygen had 1, 2, 3, 4, 5, 6, 7. I have 7 instead of 6 because the negative charge signifies that I gained 1 electron. So I just put it on this oxygen. This oxygen has 1, 2, 3, 4, 5, 6. So what's going to happen? Just like before, this electron, this lonely electron, will now bind with this lonely electron. and they will form a double bond. So you have something like that. So I'm just going to kind of clean this up like that, right? But now you might say, well, whoa, right? This is a double bonded oxygen, and this is a single bonded oxygen. That's two distinct bonds, right? But there's resonance here. There was no resonance in this compound because there was no charge, right? And also because this has a double bonded O carbon, but then this one is a oxygen with a hydrogen, so that changes the game a little bit. But in this case, we have a resonance form here because this double bonded O, right, it's just a carbon bound to an oxygen, and then it's a carbon bound to an oxygen. So could I have put the double bond here, or could I have swapped it with this? Yeah, technically the double bond could be up top, but it could also be on the right-hand side because these oxygens are absolutely equivalent. So we have to draw that structure. So it'd be H, C, C, O, H, and H. And I'm going to have this one as the single bond, and this one now has the double bond. So this will now have the 3 lone pairs because we need to keep in accordance with the octet rule, and that one has the 2 lone pairs. And that's it. Box that one off. This is a -1. So now, over here, this carbon had a double bond to oxygen. It now turned into a single bond to oxygen. This carbon had a single bond to oxygen, and now it has a double bond to oxygen. So technically, each one could exist as a double bond or a single bond or a double bond. So these have 2 forms. These are called resonance forms. But now when we actually write the hybrid is when we put the 2 forms together in one drawing, you will see that they're exactly the same. And that's why there's only 1 carbon to oxygen bond. The hybrid would be saying that I have hydrogen, carbon, carbon, oxygen, hydrogen, hydrogen. And now you say, okay, well, this oxygen could have the double bond or it could have had the single bond. But at least in both cases, it has the single bond. So that's why I draw the single bond as a clear single bond. But now it doesn't have to have the double bond, but it could. So that's when we draw half, stating that, yeah, it could have the double bond, but it doesn't have to. So it's like 50-50. And the same thing goes for the other one. Right? It could have the double bond, but it doesn't have to. So it gets that half tick for the double bond. And that is the hybrid. Your hybrid is only going to be 1 drawing. And that's how it's only 1 carbon to oxygen bond, because this is equivalent to this, as opposed to this being not equivalent to that because this has a hydrogen attached to it. So hopefully that is good to go. I'm just going to draw that they're both like this for this case because they're resonance forms of each other. All right? So that answers number 59. Hopefully you guys understand it. Let me know in the comments what you think. Subscribe to the channel if you like. We just hit 100 subscribers, so hopefully we could reach 200. That would be kind of cool. Thank you so much. Happy studying. See you all in the next question. Bye-bye.